In this lab, we explore the qualities of Newton's fundamental principle, which essentially explains how objects move with or without the application of force. In order to test this fundamental principle, an experiment was conducted in which a ball was rolled across the ground with a certain initial velocity. After comparing the experimental data with a computer model of the experiment, the results indicated that the computational model overestimated the ball's actual position. The reasoning for this result will be explained later in the presentation. Newton's fundamental principle, or Newton's second law, is as follows. The final velocity of a moving object is equal to the initial velocity plus the net force acting on that object divided by its mass times the duration. This principle remains true for all objects, including the basketball used in the experiment. In the case of the basketball, there was no force being applied. Therefore, in theory, the final velocity of the basketball should be equal to the initial velocity. Here's a clip that shows the motion of the basketball used in the experiment. In this orientation, the x-axis represents horizontal motion and the y-axis represents vertical. As time t progresses, the partitions of the basketball's movements are spaced evenly. This indicates constant velocity, which should be true, since there is no force being applied. Due to the constant velocity, the graph of position versus time is a straight line with unchanging slope. The line depicted by this graph is not perfectly straight due to possible error. It is somewhat difficult to place the tracking markers in the exact center of the basketball every single time. Also, the environment may have presented an uneven rolling surface, which would account for the imperfection of the line. The computational model was used to create the theoretical representation of the basketball's movement. Within the code, the ball's mass is indicated, as well as other aspects such as initial position and initial velocity. The initial velocity was determined by calculating the average velocity of the ball in the experiment within the first frame using this equation. The line that is highlighted is the fundamental principle itself. The net force was represented with the vector 0, 0, 0, so that the overall force in the model would remain 0. Here is the computational model in action. The ball moves in the same direction and fashion as the basketball, and the corresponding graph is nearly identical. In this graph, the blue line represents the computational model and the red represents the real-world data. When analyzing the graphs of both the computational model and the experimental data, it is clear that both graphs are not identical. The computational model overestimates the distance traveled by the ball. However, both graphs are straight lines, which indicate constant velocity and zero net force, as explained by our fundamental equation here. One explanation for this involves our calculation of the initial velocity shown here. To calculate the average velocity, we use the length of the first time frame, which was 1/30th of a second. The possible error that could have occurred is that the tracking point inserted in the first frame was not perfectly placed and therefore does not accurately represent the true overall slope of the velocity. Overall, Newton's fundamental principle is an essential tool for describing the behavior of objects in motion.